Boom. All right. So let's take a look and see what we have for you today. So Monday, hopefully last night, you went through pages 14 and 15. The answers to that are here. So if you click on that, you can see the answers to that here. Number 8 can be done 2 different ways. We'll learn a better way. I think at least students usually find it a better way on Thursday, I believe. And then I did it the way I expected you to do it last night as well, right here. I am going to do 8 and 9 in class after we're done today. If you want to stick around and see those 2, I do want to have those on the record of how to do it because they are quite difficult. Any questions on any of the others? Most of that you could probably just get like what you messed up on by going through your, like, oh, I didn't do this number or something like that. Common mistakes made for this is to not change from Celsius to Kelvin or not change back. So keep that in mind. You must be, for these laws, you must be in the absolute temperature system. Tonight's problems are these practice problems here. It's on page 18 and 19. Why we assign this is because it's starting to contain a mixture of problems. Think of the test as 30 questions. And when you read it, it's not gonna say, use this law. You're gonna have to sit there and read the information and determine what you should be using. That can be difficult. So we're gonna practice that. Then tomorrow I will not be here because none of the teachers are really Zooming tomorrow. If they are, they must have special permission or something like that because we were told to prepare our classrooms for the students coming next week. So here are the answers to the review you're doing tonight. And here's the ideal gas law, which is due Friday. And that will be the last grade that I assign you, I believe. There is something on Friday that I'll assign you and I'll grade as well. That way you guys go right into it. Oh, it's interesting. I don't have this set up right. It's a good thing that we looked at this because that means I was about to, you guys were about to email me. So we'll make this worth 30 and we will make the submission. I'm surprised that nobody was already like, that's all messed up. Oh, that's not what I want. I'll upload. That's fine. Assign to everybody. Due October 16th, which I believe is Friday. Yeah, it says Friday. All right, cool. So what you're going to do like this is it's going to be very similar to your other labs that we've done. You'll download it. All I need are these 2 sheets. So if you copy and paste this onto an assignment, or if you're doing the printout and then writing on it, all I need are those 2 sheets. I don't need the data. I'm sorry, the procedure. I just wanted you to have the procedure so you could look at it. So you're getting the mass of the magnesium, the volume of the magnesium, the temperature of the magnesium. Remember, you're collecting this in Celsius, but you need to change it to Kelvin. You're also getting the barometric pressure, but remember, since I'm capturing this gas over water, you need to subtract off that vapor pressure using that chart in the note packet. No problems here. You should be able to calculate the moles, write a balanced equation of magnesium plus hydrochloric acid, use stoichiometry to calculate the moles of gas that should form, calculate the pressure of the dry gas using the water vapor table, convert it to atmospheres, and then using the ideal gas law, calculate for R. That should be close to 0.0821. After you calculate for R, you use 0.0821 to calculate your percent air. Then you're going to assume that you have the initial pressure or temperature, and you're going to change that to STP, and you're going to solve for volume. The reason we do that is because we know at STP, 1 mole of any gas should take up 22.4 liters of space. So you're going to take the liters, the volume that you get, this V2, and you're going to divide it by the number of moles that you have of H2, and that will give you liters per mole. You're then going to use the 22.4 liters per mole, which is the known, and you're going to find the percent error there. Then using complete sentences, you will answer all of these questions. Boom, boom. That's it. Kind of fun if you want to sit here because you guys are last period of the day. You can sit here and get some practice problems done, which are not collected, and then go right into the lab after we leave this Zoom. And then you have a free day for period 10 tomorrow, right? All right, let's take a look at these problems for today. And that should be ready to set up now. Whenever you look at that, you should be able to submit one. This video, it's kind of funny.
All right.
I started massing with my old scale, but then I remembered over the summer we got this crazy scale.
Ridiculous. Look, you can see how many decimal places.
Look at how many decimal places that thing goes out.
So just to give you a quick glance, we are gonna. I mean, since I'm the only one doing this, let's just see what we can get here.
Yeah. So that's like the most specific scale that I've ever seen. And it's kind of crazy. That was donated to us by Roche Diagnostics. Most of our scales only go out 3 decimal places. This one goes out 2 more. So that's fun. It's got these little stupid automatic doors too. Watch this.
So this thing is,
like you press a button to open and close the doors. Insane.
Anybody did it.
Maybe if some of you get in here, I'll train you on how to use that. So watch the video, answer the questions. Let's take a look at what we have for today. That's obviously tomorrow with the Zoom. And it appears that I forgot how to use Canvas. So again, why are we doing these problems? So that you can sit there and figure out which formula to use. And some of these will be really quick. How many moles of gas are contained in 890 milliliters at 21 degrees Celsius and 750 millimeters of mercury pressure? Which formula are we going to want to use there? Ideal gas law or P1V1 over T1?
Ideal.
Yeah, right? How do you know, Henry?
It's asking for moles.
The fact that it asks for moles right there tells you PV equals nRT. Those few things. If I want to use the R of 0.0821 atmosphere liters per mole Kelvin, I've got to do some work here. I've got to change this from millimeters of mercury to atmospheres. 750 divided by 760.
It's about 0.9868.
I've got to change this to, excuse me, I've got to change this to Kelvin. 21 plus 273.15.
It's 294.15.
So that's only significant to that first decimal place, right? And I got to change this 890 milliliters into what? Liters. Does anybody remember how I do that? I can move the decimal place over 3 times or divide by 1,000. 0.8900 liters.
Technically, could you use one of the other R values that's not, if you didn't want to convert?
The only one I wouldn't have to convert is atmospheres. I could use 62.4, but I still have to convert milliliters to liters and Celsius to Kelvin. Are you going to memorize all 3 R constants so you don't have to convert? That's fine. Doesn't matter. Then we would just rearrange this equation. Number 2, what would we use for number 2? PV equals nRT, P1V1 over T1 equals P2V2 over T2. A sample of oxygen gas at 30 degrees Celsius fills a 50-liter volume. If the temperature is raised to 50 degrees Celsius and the pressure is held constant, what volume will the same sample occupy? Ideal or combined? Pervnert or
Combined.
Combined gas law. Good. Do we need all the variables or can we cross one out?
time can be crossed out. Not time, sorry.
Pressure.
Pressure. P1 equals P2. You feel pressured by time constraints. Your mind was on time there. P1 equals P2, so we don't have to put it into it, right? 3, if 1.09 grams of H2 is contained in a 2-liter container at 20 degrees Celsius, what is the pressure in this container in millimeters of mercury? Who's my student of the month? This is almost a student of the month question right here too. PV equals nRT, or P1 V1 over T1 equals P2 V2 over T2.
PV equals nRT.
Yes, PV equals nRT. Oh, is this a challenge for student of the month right before the end, right? Why can you use PV equals nRT?
You have the how did I say it? Losing my train of thought here. Okay.
Oh, who is the prospect student of the month from yesterday? You want to take over for him? Are they not here today? Oh, is it Emily? Or was it? Yeah. No. She's gonna let you have it, Henry.
I don't. I think it's. Is it because you have the you already have the moles?
Where are the moles?
No.
Where are the moles? I don't see the moles here.
Is it because it's grams of hydrogen?
What can we do with that?
You can convert it to moles and then number of particles.
Do we need, yeah, moles is number of particles, but that's exactly right, right? If we have the grams of hydrogen, we can use the periodic table. Every 1 mole of hydrogen has a mass of 2.02. So that right
So
there.
if moles is involved in the equation, then do we know we have to use PV equals nRT?
You got it, unless they really put a tricky one in there and said, hey, by the way, we have this many moles, even though you don't need to use it, right? But yeah, and that's why this one's tricky. It doesn't say moles, but it has grams, which a few people probably saw that from grams you can get moles. So right there, so that's how we would get our N. Samantha, I think a better way to say it is if you have multiple temperatures, volumes, or pressures. If you have a change in one of those things, then you know you're using the combined gas law. But by looking at both of those things, then nothing's going to get by you. Nothing's going to get by you at all on that. Cool. So let's go ahead. That's all I've got for you. That's what you're going to be doing tonight, and you're actually going to go through and solve those. If you want to hang out, and I'm going to go through problem 8 and 9, and we'll answer questions on that. These problems are a little bit difficult. If you're like, nah, I got them, they were easy, get out of here, it's fine. Otherwise, if you have a question other than these two, we can wait until after I solve these two. But, all right. So the density of oxygen gas is 1.14 grams per liter. If 5 grams of oxygen exert 2 atmospheres of pressure, what is the temperature in degrees Celsius of this gas? So just like the last one, right here, the fact that we have this 5.00 grams of oxygen, we have to remember that that is oxygen gas and it is diatomic. So we have to go O2. Every 32.00 grams is 1 mole. So that right there gets us to moles. 5 divided by 32.
It's about 0.1562.
So that's how many moles we have. This would have 3 significant digits. I'm going to go ahead and underline those. So that's my N. This is my P. I'm trying to find T. So if PV equals nRT, we want to rearrange this equation to solve for T. So N and R cancel out. So I have the P is 2.00 atmospheres. Oh no, V, I need V. But this is density. And if you recall, density equals mass over volume. So if I have the mass, 5.00 grams, if I take density equals mass over volume, to get volume, we take the mass and we divide it by the density, 1.14 grams per 1 liter. 5 divided by 1.14,
It's about 4.3859.
liters. Again, that would have 3 significant digits as well. And the atmospheres has 3 significant digits. So it looks like we're probably going to have 3 significant digits for our final answer for this. So 2 atmospheres, that many liters. Down here, we have the number of moles, 0.15625 moles. And our R constant, 0.0821 atmosphere liters per Kelvin mole. Again, moles are on bottom, and then on bottom of the bottom. Atmospheres on top of the top and on top of the bottom, so that will cancel out. Liters is on top of the top and top of the bottom, so that would cancel out. Kelvin is on bottom of the bottom, so that really means that it's on top. The inverse of an inverse thing. 2 times 4.38596 divided by 0.156, too slow. 2 times 4.38596 divided by 0.15625 divided by 0.0821.
It's about 683.8037.
So 683.8 Kelvin. 683.8 minus 273.
It's 410.8.
So that brings us to 411, it looks like, degrees Celsius. So they got 413 probably because of them rounding this to 4.39 or something like that. I am comfortable enough with this, 411, by looking at how close that is. I didn't round until the very end. They may have rounded before that point. So that's how you do that one. If we take a look, a sample of solid potassium chlorate decomposes and produces solid potassium chloride, +1, -1, so that's the formula, and oxygen gas. But we have to remember oxygen gas is diatomic. Somebody help me balance that. What do we do to balance it?
2, then 2, then 3.
2, 2, 3, good. 2, 2, 3, 6, 6. Very nice. This is in milliliters. If I want to use my K value, I'm going to have to use liters. So 0.675 liters. 22 plus 273.15.
The answer is 295.15.
So 295.15 Kelvin. 754 divided by 760.
That would be about 0.9921.
Three significant digits on that as well. So I have my volume, I have my temperature, and I have my pressure. I want the number of moles of oxygen gas because I know it takes, for every 3 moles of oxygen gas, it takes 2 moles of potassium chlorate. So if I want to find out how much potassium chlorate it takes, every 3 moles of O2 requires 2 moles of KClO3. So PV equals nRT. We want to solve for N. So 0.99211 times 0.675 divided by 295.15 divided by 0.0821.
The answer is about 0.02763.
So that's the number of moles of O2. So 0.02764 moles of O2 Every 3 moles of O2 requires 2 moles of KClO3 using stoichiometry. And every 1 mole of KClO3 3 times 16 plus 39.10 plus 35.45
It's 122.55.
is 122.55 grams from the periodic table. 0.02764 times 2 divided by 3 times 122.55.
The answer is about 2.2581.
2.26 grams. So I used the PV equals nRT to find the number of moles. I plugged the moles into a stoichiometric relationship problem to go from moles of O2 to moles of KClO3. I then used the molar mass from the periodic table to convert from moles of KClO3 to grams of KClO3. Any questions there?